I want to start this by reminding us of the results that we got in a previous video. All right, for a given reaction, and this is our hypothetical reaction written here at the top, we're going to assume that we're starting with an equilibrium at temperature T1. Now we've seen that the Van 't Hoff equation gives us a way of measuring the change in the equilibrium constant when it changes from one temperature to another, and it's simply given by this equation here. And we're going to use this equation to learn a little bit more about how reactions respond to changes in temperature. Now I want to note that we're going to generally, in this case, allow the second temperature, T2, to be greater than T1, which means that 1 over T1 is greater than 1 over T2. So this is a positive quantity here in parentheses. And so what that really means is that since all of this is going to affect the delta G for the reaction, we're going to really care what the sign is of this delta H. Is it an exothermic reaction or an endothermic reaction? All right, so let's now get to a direct examination of delta G. We know from earlier studies that delta G can be written as RT times the log of the ratio of the reaction quotient to the equilibrium constant. All right, so what does that mean in this particular case? I've got a reaction that starts at equilibrium at T1. So that means in some sense initially I have Q is equal to the equilibrium constant at temperature T1. We're at equilibrium. The Q is going to equal the equilibrium constant when we're at equilibrium, so this will be true. But we're going to move to a state where we have a new equilibrium constant, and the new equilibrium constant is going to be at temperature T2. And initially, at least, Q will not be equal to that. So if I want to use this change process in my evaluation of this logarithm, what that means is that I'm going to be calculating RT log, and now Q is still stuck at its initial value, K of T1, and it's going to be divided by the new K, K of T2. Now I'll note that since we've changed the temperature to a value of T2, that means this temperature here must be T2. So I'm going to have this relationship also. All right, so I can make this look a little bit more like the Van 't Hoff equation by taking the negative of this. If I put a negative in front, I can switch the numerator and denominator here in the log function. So I'll have negative RT2, the logarithm of KT2 divided by KT1. And now that will look a lot like this quantity here. But now, since I know what this quantity is from the Van 't Hoff equation, I can just substitute this part in for the logarithm here. So in other words, this whole thing is going to be negative RT2. And now I'm just going to make that direct substitution. I'm going to have delta RH0 over R delta H, and 1 over T1 minus 1 over T2. Okay, now when I go through and do this multiplication, these factors of R are going to cancel each other. And I'm going to bring this factor of T2 in here. So I'll end up with an equation that looks something like this. I'll keep it in purple. All right, I'll have negative the enthalpy change for this reaction times the quantity T2 divided by T1 minus T2 over T2, which is just 1. All right, so, and this is, mind you, equal to the Gibbs energy change for this reaction. All right, so this is actually more or less the result that we needed to get to in order to evaluate what happens to this reaction when I increase the temperature to T2, because it's giving us a way to figure out what the sign of delta G is going to be. So I have basically two conditions here. Okay, one condition is that I have an endothermic reaction. And an endothermic reaction, that means that the delta H of the reaction is going to be greater than 0. Okay, we add heat to the reactant mixture. And so when I do that, what does that mean for delta G? Well, if delta H is greater than 0, delta G here must be less than 0. So delta G will be less than 0 in this case, which means that this reaction should proceed spontaneously to the right. Okay, what about in the case of an an exothermic reaction? Well, I think we can reasonably expect that it's going to be the opposite effect, right? If delta H is less than 0, now this is a negative quantity here, so I'm taking negative of a negative quantity, which means that my delta G at the end of the day is going to be greater than 0. So in other words, I will have a spontaneous change that will go in this direction on the reaction. I'm now favoring the reactants from this. All right, so in effect, what we're saying here is that for an endothermic case, we're going to favor products by increasing the temperature. For an exothermic case, we're going to favor reactants. Now let's see what this looks like if we were to draw it out diagrammatically. So on this page, what I have are two diagrams, one of them representing an endothermic reaction and one of them representing an exothermic reaction. And this is just a reaction energy diagram where I'm drawing enthalpy as the vertical coordinate, and the horizontal coordinate is just a reaction coordinate that tells us something about the progress of the reaction. All right, so when I look at an endothermic case, okay, what we decided was that when we increase the temperature, we're going to favor something that goes to the right. Okay, and when we have an exothermic reaction, which is shown in the second diagram, and we increase the temperature, we're going to have a reaction that favors going to the left. All right, so what's consistent about these? Well, in both cases, increasing the temperature has basically favored a shift toward the side of the reaction that has a higher enthalpy content. So one way we can summarize the effect in this case is that increasing the temperature favors the side with higher enthalpy content. So I think you can imagine what will happen if we decrease the temperature, and it's actually drawn here in blue. When I decrease the temperature, it's actually the opposite effect in both of these cases. Decreasing the temperature for the endothermic reaction will favor formation of more reactants. Decreasing the temperature for the exothermic reaction will favor the formation of more products. So we can say that the contrast to this is that decreasing temperature favors the side with lower enthalpy content. All right, so by applying this very simple thermodynamic analysis, we can make sense of the Le Chatelier's principal rule for changing the temperature of a reaction. And I'll remind you that one of the mnemonics that we often teach in general chemistry looks like this up here, that if we add heat as one of the components of the reaction, that increasing the temperature is like adding heat. And so if I add heat, Le Chatelier's principle says I'm going to shift away from the heat. If I add heat on the product side, I'm going to shift away from the heat. So that's consistent with what we're seeing here for these red arrows in the lower diagram.